Space is a living fabric, not a silent void, but a dynamic tapestry that stretches, twists, and remembers everything that moves through it. When stars collide, galaxies dance, or planets bend light, space-time ripples and reshapes itself in real time. In this video, we'll explore how the structure of space acts like living matter, responsive to mass and energy, shaping the paths we call distance, and writing the history of the cosmos into its folds. We'll move from the equations that govern gravity to vivid visuals that reveal how time, geometry, and motion are entwined. This isn't abstract math. It reframes what reality is made of and how the universe really works, right down to the fabric you and first travel through every day. Ready to hear the heartbeat of the cosmos and see space come alive? The concept of space as a living fabric. Space-time is described by geometry, not a tangible substance, yet it responds to mass and energy. The Einstein field equations tie the curvature of space-time to the energy-momentum content that fills it, so gravity becomes the result of geometry, changing in response to matter. In practical terms, light follows curved paths around massive objects, and clocks tick differently where gravity is stronger. That bending of light and the stretching of time are everyday demonstrations that space behaves like a living medium, reshaping itself as conditions change. Gravitational lensing maps mass, including dark matter, by how it warps light from distant sources. Some theories suggest space is not a fixed stage, but a structure that emerges from deeper quantum rules. Spin networks in loop quantum gravity describe space as a network of discrete quanta connected by links that encode areas and volumes. There are approaches where space-time is built from entanglement patterns, suggesting a holographic link between boundary information and bulk geometry. In these views, the fabric acts as a dynamic, information-bearing medium that can rearrange itself when energy is rearranged. This is less about a material substance and more about relational structures that define distances and connections. Gravitational waves reveal the fabric's waviness. Detectors measure tiny distortions as space stretches and squeezes. The discovery of gravitational waves showed space-time is actually dynamic, not a passive backdrop. Cosmological redshift demonstrates space itself expands, increasing the distance between distant galaxies over time. Gravitational lensing helps locate dark matter by how space bends light. These observations anchor the view of space as an active participant in cosmic evolution. The living fabric is a metaphor that captures responsiveness, not aliveness. Space is not a substance floating in a void. It is a four-dimensional geometry described by a metric. Measurements like the curvature tensor, the metric, and connection coefficients are how we quantify its properties. The cosmological constant or dark energy acts as a driver of expansion, changing distances even in the absence of local mass energy. Ultimately, the fabric perspective guides modeling of gravitational physics, quantum gravity attempts, and astronomy, geometry, curvature, and the language of space. In general relativity, space-time is a four-dimensional fabric whose geometry is described by a metric tensor that tells you how distances and times fit together. The curvature of that fabric is produced by energy and momentum, shaping how objects move. This curvature is intrinsic, measurable through clocks and rulers, and it does not require an imagined embedding in any higher space. Light follows null geodesics and bends around masses, creating gravitational lensing. A planet in free fall traces a geodesic in curved space-time, which translates into the familiar orbits we describe in everyday terms. The mathematics centers on the Riemann tensor and the Einstein field equations g mu nu equals 8 pi g / c caret 4 t mu nu tie curvature to energy and momentum. The language of geometry is the metric itself, the rule that assigns a distance between any two events. From that rule, curvature emerges when the metric changes from place to place. Curvature is described by the Riemann tensor, with contractions forming the Ricci tensor and the scalar curvature that tell us how volumes deviate from flat space. In vacuum, the whale part carries tidal information about how neighboring geodesics converge or diverge. Free-falling observers experience proper time along their world lines, and geodesics maximize or extremize this time in the absence of non-gravitational forces. Gravitational time dilation makes clocks tick slower in stronger gravity. These statements are not abstract. They operate in laboratories, in satellites, and in the light we receive from distant stars. Observations reveal geometry at work across vast scales. Gravitational lensing magnifies and distorts the light from background galaxies, mapping unseen mass. Time dilation shifts the frequencies of signals and the rate of ticking clocks as gravity varies along their path. GPS satellites must account for these effects to deliver precise positioning. Gravitational waves are ripples in space-time produced by accelerating masses, and detectors have measured these tiny strains when cosmic events unfold. On cosmic scales, the expansion of space is encoded in the metric that evolves with time. The large-scale curvature seems nearly flat, though small deviations are subjects of active inquiry. Space is not a passive stage, but a living medium that responds to energy. Geometry guides motion by telling objects how to move along curves called geodesics. Light, matter, and even clocks read the same language as they traverse the curved fabric, translating geometry into physical effects. Frame dragging shows how rotation twists spacetime around a body and alters nearby inertial frames. The language of space also involves topological and causal structure, which restricts how regions influence one another. Understanding this fabric informs experiments, astrophysical interpretations, and the search for physics beyond Einstein. Dynamics of the fabric, waves, interactions, and turbulence. Spacetime is a dynamic fabric described by Einstein's equations, not a fixed backdrop for events. The metric that defines distances and durations changes in response to energy and momentum, so geometry and matter are interwoven. Gravitational waves are distortions of this fabric that propagate at the speed of light, carrying information about their source without carrying matter along with them. When compact objects like black holes or neutron stars dance and merge, the fabric wears a visible ripple pattern that travels outward. Detectors such as laser interferometers measure tiny strains as these waves stretch and compress spacetime along their paths. Waves propagate on a curved backdrop and bend around mass concentrations, altering their paths. The energy they transport feeds back into the geometry, but in ordinary settings this back reaction remains tiny. In strong field regions, nonlinearities allow wave components to interact and modify each other's phase and amplitude. Such interactions are expected to be weak for most astrophysical events, yet they become relevant when waves are intense or when the geometry is highly dynamic. The result is a pattern that is not a simple propagation but a dialogue between waves and the curvature they traverse. Chaotic, turbulence-like behavior can emerge in nonlinear GR under certain conditions. Small disturbances can transfer energy across scales, generating a spectrum of curvature fluctuations. In theory, this can lead to a cascade where large-scale features feed smaller-scale structure in the fabric. Numerical simulations reveal complex, persistently evolving patterns in strong field, confined systems. These patterns resemble turbulence in fluids, but they are curvature-centric. This turbulence is not universal. It depends on the boundary conditions and the presence of fields other than gravity, such as scalar or electromagnetic fields. Gravitational waves enable a new kind of cosmic seismology, letting us map how spacetime responds to mass dynamics. The memory effect leaves a lasting imprint after a wave has passed, a permanent displacement in the fabric that survives the transit of the signal. Gravitational lensing of waves and light demonstrates how spacetime geometry shapes propagation, magnifying or distorting contractions and expansions along the path. Understanding the fabric's dynamics helps interpret signals from mergers and informs tests of general relativity. In the future, observations of stochastic backgrounds or high-frequency components could reveal turbulence-driven features and the intricate choreography of spacetime under extreme conditions. Emergence of particles and fields from living geometry. Space can be modeled as a dynamic geometric medium in which waves, particles, and interactions ride on the curvature and connectivity of the fabric itself. In several lines of thought, particles and fields emerge as collective excitations of this living geometry. A concrete and widely cited analogy comes from graphene, where the honeycomb lattice endows electrons with massless Dirac-like behavior that mirrors relativistic dynamics. The effective velocity is far below the speed of light. Strain in the lattice can produce pseudomagnetic fields that bend electron trajectories as if real magnetic fields were present, without breaking time reversal symmetry. Fields emerge when the geometry carries connections and curvature that couple to wave-like excitations, acting as if gauge forces live in the medium itself. Dislocations and twists can mimic flux tubes and gauge strings. In Weyl and Dirac semimetals, low-energy excitations behave like relativistic fermions and respond to geometric deformations as emergent gauge phenomena. Topological insulators add surface states protected by geometry. In quantum spin liquids, the entangled geometry can host emergent gauge fields and fractionalized excitations such as Majorana modes, offering a window into how geometry and particle-like entities co-emerge. Beyond solids, the idea that space itself could arise from quantum information ties geometry to entanglement networks, where distance becomes a measure of information connectivity. Tensor network models reproduce geometric features and hint at deep links to holography. The holographic principle and ADS/CFT illustrate how a higher-dimensional geometry can encode the behavior of lower-dimensional quantum fields, suggesting that particles may be manifestations of deeper geometric relations. Entanglement patterns can, in principle, determine curvature. Experimental platforms using ultra-cold atoms, programmable spins, and cold atom simulators create tunable geometries where excitation spectra resemble gravitational and gauge-theoretic entities, offering practical leverage to test ideas about emergent spacetime. Analog gravity experiments translate curved space ideas into accessible laboratory setups using fluids, Bose-Einstein condensates, or metamaterials to mimic horizons, redshift, and wave propagation in curved backgrounds. These systems show that geometry controls dynamics, even when the underlying medium is not spacetime itself. Transformation optics and gradient index metamaterials demonstrate how shaping a medium steers waves as if space were curved, correlating with the concept that living geometry supports particle-like and field-like excitations. Designs in graphene and other layered materials already exploit geometry to create excitations that behave like relativistic entities. The practical takeaway is that emergent particles and fields can be viewed as manifestations of a responsive geometric fabric, where observation, measurement, and material architecture co-create what counts as a particle and what counts as a field. Cosmological implications and the nature of reality. Space is not empty, but a dynamic fabric described by spacetime. Its curvature is determined by energy and momentum, a relationship codified in Einstein's field equations. The fabric stretches and bends, guiding the motion of matter and light and revealing gravity as geometry rather than a force in the traditional sense. Gravitational waves are ripples that travel across the cosmos, carrying information about violent events and the evolving structure of spacetime itself. The cosmic microwave background remains a fossil glow, a snapshot of the universe when the fabric was smoother. Space continues to expand, a process that interacts with curvature to shape large-scale geometry, while dark energy injects a push that accelerates this expansion today. From this perspective, space is not a passive stage, but a physical medium woven by energy and fields that permeate every region. Quantum fluctuations in the vacuum are not mere emptiness. They seed tiny density variations that gravity can amplify into galaxies and clusters. During periods of rapid expansion, these fluctuations are stretched to cosmic scales, leaving an imprint in the fabric that later becomes the pattern of galaxies and voids we observe. The global shape of space could be finite or infinite, and its topology might wrap around so that traveling far enough could bring you back to your starting point. The content of space itself, how energy density, pressure, and geometry intertwine, determines how curvature evolves over time and how the universe responds to its own contents. Relating these ideas to the nature of reality prompts deep questions. Local experiments reveal causal relationships, But large-scale correlations remind us that geometry and matter are not isolated but entwined. Entanglement and information theory hint at a universe where reality is not reducible to isolated events but emerges from networks of relationships. The holographic principle suggests information within a volume could be encoded on its boundary, offering a different lens on how reality might be encoded. Observations of the cosmic microwave background polarization and gravitational lensing map the choreography of light and matter as the fabric curves. Our measurements test whether the fabric behaves like a classical stage or exhibits quantum features on cosmological scales. Practically, these ideas guide experimental programs. Gravitational wave detectors listen to space-time itself, opening a new window into the dynamics of the cosmos. Astronomers map lensing to infer mass distribution and test gravity on large scales. Studies of the CMB and the distribution of galaxies probe the universe's geometry and fate. The notion of space as a living material drives ongoing debates about emergent gravity, quantum cosmology, and the possibility that reality itself is relational. As instruments sharpen, we draw closer to understanding whether reality is carved out by observation, or if space-time holds independent existence beyond perception. We've traveled a path through the fabric of space, viewing space as living matter rather than a blank stage. The core ideas are simple to repeat. Space-time is a dynamic, woven fabric that carries energy and information. Mass and energy bend this fabric, making gravity a geometric feature. The fabric can ripple through gravitational waves. At the smallest scales, quantum ideas hint at a texture beneath smoothness, and cosmic expansion stretches the fabric, guiding the evolution of the cosmos. Taken together, space feels alive, responsive, interconnected, and full of activity that writes the history of everything we observe. Perhaps you felt this while staring at the night sky, an invitation to see the universe as a living, listening structure rather than a distant backdrop. If this sparked your curiosity, consider liking, subscribing, and tapping the bell so you don't miss the next chapter. Share this with a friend who loves big questions, too. Next, we'll dive deeper into gravitational waves, their origins, how we detect them, and what they tell us about black holes and neutron stars. After that, we'll peek at ideas from quantum geometry and what space's possible texture might mean for physics and exploration. Until then, keep looking up and listening for the fabric's quiet hum. The adventure of understanding the universe is just beginning.